Today I'm going to continue my previous lecture on Nesterov smoothing. Our goal is to find smooth approximations for non-smooth functions. As you can see from the previous lecture, many non-smooth functions can be written as follows. F of x is the supremum of the inner product of ax and u minus 5 of u, where u runs in Rm. Here, A is an n by n matrix, and 5 from Rm to the extended real line is proper, lower semi-continuous, and convex. From the definition, we can see that f of x is equal to phi star of ax for all x in Rn, where phi star is the Fenchel conjugate of 5. And in the case where A is the identity matrix, we can see that f is just phi star, that is the Fenchel conjugate of 5. To move on, I would like to recall an important result. If h from Rn to the extended real line is proper, lower semi-continuous, and strongly convex with parameter sigma greater than 0, then its Fenchel conjugate is a C11 function. It means that a star is a C1 function and its gradient satisfies the Lipschitz condition in the sense that the Euclidean norm of the gradient of a star at x minus the gradient of a star at u is less than or equal to 1 over sigma times norm of x minus u, and this is true for all x and u in Rn. Okay, so a star is C11 function, and we can also put 1 over sigma here to be precise. We will also need the following simple proposition. Let 5 and 3 be extended real value functions, where 5 is proper, lower semi-continuous, and convex. If 3 is a proper, lower semi-continuous, and a strongly convex function, where the strongly convex parameter is sigma, and if we assume that the domain of the function 5 intersection the domain of the function 3 is non-empty, then the sum of 5 and 3 is proper, lower semi-continuous, and strongly convex with the same parameter sigma. It means that if you add a strongly convex function to a convex function, then the new function is strongly convex. Okay. Now the second part is as follows. If T is proper, lower semi-continuous, and strongly convex with parameter sigma, then mu times 3, where mu is a positive constant, is proper, lower semi-continuous, and strongly convex with parameter sigma times mu. That means if you multiply a positive constant to a strongly convex function, then the new function is strongly convex as well. Now I'm going to sketch the proof of this proposition. So for the first part, how come the sum of 5 and 3 is proper? This fact is very simple to prove because we assume that the domain of the function 5 intersection the domain of the function 3 is non-empty. So you can find some x in that intersection. Okay, and for that x, 5 of x is a real number, and 3 of x is also a real number. So 5 plus 3 of x is a real number. So the sum of 5 plus 3 is proper. Okay, so this is based on the fact that the intersection of the domain of 5 and the domain of 3 is non-empty. Okay. And how come the sum is lower semi-continuous? This is also well known because the sum of two lower semi-continuous functions is a lower semi-continuous function. You can watch my video lecture on lower semi-continuity to find out more about it. Okay. Next, we are going to prove the main part, that is the sum of 5 and 3 is strongly convex. How come that is true? Okay, so because G is strongly convex with parameter sigma. As you can see from the definition, G minus sigma over 2 times the square norm function. This function is convex. Okay. Now, because 5 is a convex function, you're gonna see that 5 plus G minus sigma over 2 times the square norm function. This function is convex as well. Okay. Why? The sum of two convex functions is a convex function. So this is in fact 5 plus G minus sigma over 2 times the square norm function. Okay, so by the definition, this function minus this function is convex, and therefore 5 plus G is strongly convex. So by the definition, and from here you can also see that this function is strongly convex with parameter sigma. For the second part, I omit the proof that mu times G is proper and lower semi-continuous, given that G is proper and lower semi-continuous, because those facts are very elementary. Now I'm going to prove that if G is strongly convex with parameter sigma, then mu times G is strongly convex with parameter sigma times mu. Okay, so by the definition, you see that G minus sigma over 2 times the square norm function is convex. Okay. So from here, a very simple fact that if you multiply a convex function by a positive constant, you're gonna have a convex function. Okay, so because mu is greater than 0, you're gonna see that mu times G minus sigma over 2 times the square norm function here is convex as well. Okay, and therefore mu times G minus sigma mu over 2 times the square norm function is convex. Okay. So from here you can see that mu times G minus this constant times the square norm function is a convex function. So by the definition of strong convexity, this function is strongly convex. And the parameter is sigma times mu from here. Okay. Okay, so the proof is complete. Now I am getting to the main part of the lecture on Nesterov smoothing. To make the presentation easy, at first I'm going to talk about simple smoothing. The main idea is that we only consider the case where f is just the Fantel conjugate of a function 5, where 5 is proper, lower semi-continuous and convex. And again, from my previous lectures, you can see that many non-smooth functions can be represented in this form. And again, our goal is to find a smooth approximation of the function f of this form. The smoothing procedure goes through two steps. In the first step, we are going to find a family of smooth functions based on the structure of the function f. We are going to fix a function d, which is proper, lower semi-continuous and strongly convex with parameter sigma greater than 0. The strong convexity is really important in this procedure. And we have to guarantee that the domain of the function 5 and the domain of the function d intersect each other. Now, given a positive parameter sigma greater than 0, we define the function f sub mu by the following formula. F sub mu of x is the supremum of the inner product of x and u minus 5 of u minus mu times d of u, where u runs in Rn. So it is based on the function f. So the function f is the supremum without this part. So from the definition of the function f, we only need to subtract mu times d of u, where again d is this function that is proper, lower semi-continuous, and strongly convex with parameter sigma. So if you remember the definition of the Fantel conjugate of a function, you can see that this is actually the supremum of the inner product of x and u minus what? Minus phi plus mu d of u, where u runs in I. Okay? Therefore, this is exactly the Fantel conjugate of phi plus mu times d. Okay, so f of mu is nothing but the Fantel conjugate of the sum of phi and mu times d. Okay. Now, the conclusion is that f of mu is a C11 function, and the gradient of f of mu is Lipschitz continuous with Lipschitz constant 1 over sigma times mu. How come this is true? It's very, very simple. Okay. Now, from the previous proposition, we see that because d is strongly convex with parameter sigma, mu times d is strongly convex with parameter sigma times mu. Now you add a convex function 5, the new function here is still strongly convex with parameter sigma times mu. Okay, and the new function is also proper and lower semi-continuous given these assumptions. Okay, therefore its Fantel conjugate is C11, and the Lipschitz constant of the gradient of f of mu is Lipschitz continuous with constant 1 over sigma times mu, 1 over the strong convex parameter of the function. So you have seen that we are able to build a family of smooth functions based on the function f. To illustrate the first step, I'm going through a very simple example. The example under consideration is the absolute value function. How can you make the absolute value function smooth? Okay, so in this situation, f of x is the absolute value of x. And as you can see from my previous lecture, f of x can be written as x times u, where u runs in the interval minus 1, 1. Okay, so this is also the supremum x of x times u minus the indicator function associated with the interval minus 1, 1 at u, where u runs in R. And this is actually the Fantel conjugate of the indicator function associated with the interval minus 1, 1 at x. Okay, so based on the procedure developed in the first step, how can we build f mu of x? So given a positive constant mu, we define f mu of x by subtracting mu times a strongly convex function from here. And the strongly convex function we are going to use is very simple. D of u is 1/2 times u squared. This function satisfies all of the conditions given in the first step. Okay, so f of mu is the supremum of x times u minus 1/2 times u squared and you multiply by mu. So mu over 2 times u squared, where u runs in the interval minus 1, 1. Okay, so it is very easy to see that f of mu from the previous step is given in this way. The supremum of x times u minus mu over 2 times u squared, where u runs in the interval minus 1, 1. How can we find this supremum? The problem now reduces to a very simple calculus problem. We are going to maximize the function g defined in this way. G of u is x times u minus mu over 2 times u squared, where u runs in the interval minus 1, 1. To maximize this function, we are going to compute its derivative, which is x minus mu times u. This is the derivative with respect to u. So the critical, we can see that when we apply the Fermat rule to this function, the critical number is x over mu. In the first case, where x over mu is greater than or equal to minus 1 and 1, we see the following situation. So this is x that runs from minus 1, I'm sorry, this is u that runs from minus 1 to 1, and this is x over mu. As you can see, if u runs from minus 1 to x over mu, the derivative of the function is positive. And from here to here, the derivative of the function is negative. Okay, so the function g has an absolute maximizer, which is x over mu. Okay, so in order to find the function f, we only need to replace u by x over mu in the function g. So f mu of x is x times u, which is x over mu, minus mu over 2 times x over mu squared. And you can easily see that this is x squared over 2 mu. In the case where x over mu is less than minus 1, we have the following table. So this is x over mu, this is minus 1, and this is 1. And remember that we only consider u in the interval from minus 1 to 1. You can easily see that in this interval, g prime is always negative. Therefore, the function g is monotone decreasing. Therefore, t has an absolute minimum at minus 1. In order to find f mu of x, we only need to replace u by minus 1. So f mu of x is x times minus 1 minus mu over 2 times minus 1 square. So f mu of x is equal to minus x minus mu over 2. Okay. Now there is one more case. That is the case where x over mu is greater than 1. Okay, so you can easily see that in this case, the function t has an absolute maximizer at 1, and therefore f mu of x is equal to x minus mu over 2. Okay, so to conclude, we see that f of mu is given by the following formula. So f mu of x is equal to x squared over 2 mu, x squared over 2 mu if the absolute value of x is less than or equal to mu. Okay. and then it will be x minus mu over 2 if x is greater than mu, and it's minus x minus mu over 2 if x is less than minus mu. Okay, and if you plot this function, you can see that f of mu is a differentiable function. We can also see that f of mu can be represented in a simpler form. F of mu of x is equal to x squared over 2 mu if the absolute value of x is less than or equal to mu. And it's the absolute value of x minus mu over 2 is if the absolute value of x is greater than mu. Now I am going through the second step of Nesterov smoothing. And in the first step, we have seen that using a proper lower semi-continuous and strongly convex function D, we are able to build a family of smooth functions. However, how can we guarantee that not family of smooth functions gives smooth approximations for the function f under consideration? To accomplish that goal, we have to make sure that D satisfies more properties as given below. A function D is called a proximity function for the function f if the following conditions are satisfied. The first condition is that D is proper lower semi-continuous and strongly convex with parameter sigma. So this is nothing but just the condition given in the first step. Okay, and this is another important condition. The domain of the function 5 has to be a subset of the domain of the function D. So the domain of the function D has to be large enough to include the domain of the function 5 where f is the Fancel conjugate of 5. The third condition is that D of x is greater than or equal to 0 for all x in Rn. So D is a non-negative function. And the final condition is that the supremum of D of x, where x runs in the domain of the function phi, has to be less than infinity. And we denote that constant by D. Okay. By the way, under this condition, we can see that the intersection of the domain of the function 5 and the domain of the function D is just the domain of the function 5, because this is a subset of this. Okay, and therefore this is non-empty because we assume that 5 is a proper function. So in fact, from the first condition, we can see that D satisfies all conditions given in the first step. Now, recall that f of mu is defined as follows. F of mu is just the Fancel conjugate of the sum of 5 and mu times D. Under more assumptions on the function D given in the definition of the proximity, you're going to see that this new condition is satisfied. That means f mu of x is always less than or equal to f of x and less than or equal to f mu of x plus mu times D, and this is true for all x in Rn. This guarantees that f mu is in fact a good approximation of the function f. Imagine that given any value of x, if you pick mu small enough, then f of mu of x is close to f of x. And recall that D is this constant. D is the supremum of D of x, where x runs in the domain of the function phi. And as we can see from the first step, f mu is a C11 function, and the gradient of f of mu is Lipschitz continuous with a constant 1 over sigma times mu. Now I am going to prove that the approximation inequalities presented earlier is satisfied. So recall that f mu of x is equal to the supremum of the inner product of x and u minus 5 of u minus mu times d of u, where u runs in Rm. I'm sorry, this is Rn. Okay. So remember that this is equal to the supremum of the inner product of x and u minus 5 of u minus mu times d of u, where u runs in the intersection of the domain of the function 5 and the domain of the function d. How come this is true? This is very simple, because if u is not in this intersection, then either 5 of u is infinity or d of u is infinity. So this sum does not contribute to the supremum. Okay, so but because d is a proximity function for the function f, the domain of the function 5 here is a subset of the domain of the function d. So this intersection is actually the supremum of the inner product of x and u minus 5 of u minus mu times d of u, where u runs in the domain of the function 5. Okay, so again, this is true because the domain of the function 5 is a subset of the domain of the function d. Now, because d of u is greater than or equal to 0, this is less than or equal to the supremum of the inner product of x and u minus 5 of u, where u runs in the domain of the function 5. And what is it? This is f of x. Okay, and this is actually phi star of x. Okay, so we have seen that f mu of x is less than or equal to f of x for all x in Rn. To continue, we start from the formula for f of x. F of x is just phi star of x, and this is again the supremum of x u minus 5 of u, where u runs in the domain of the function 5. Okay, so now this is equal to the supremum of the inner product of x and u minus 5 of u, and then we subtract mu times du, and we add mu times du, where u runs in the domain of 5. Okay, so this is less than or equal to the supremum of the sum. So it's less than the sum of the supremum. So the supremum of this inner product where u runs in the domain of 5, and then we add mu times the supremum of d of u, where u runs in the domain of 5 as well. Okay. Now, from the previous calculation, we already saw that this is exactly f mu of x. So this is f mu of x, and this is mu times this supremum, because d is a proximity for f. We have that this is a positive constant, a real number. Okay, so this is d. From this, from the proof, we conclude that f of x is always greater than or equal to f mu of x, and f of x is less than or equal to f mu of x plus mu times d, and this is true for all x in Rn. Okay, so this is a very important approximation, and this approximation guarantees that f mu is a good approximation of the original function f, and f mu is a C11 function, which is very favorable for applying numerical optimization techniques.